Good afternoon, and welcome to COMSO Multiphysics Introduction to Structural Mechanics module. I'm Hakam Al-Asawi, Technical Support Engineer at Nadi Engineering and Agencies. We are the sole distributor of COMSO Multiphysics in the Arab countries. Today, we're going to talk about the COMSO Multiphysics Structural Mechanics module, and after that, we're going to have a brief demonstration session of the module in action, use some of the features and use some of the multiphysics features in the module and the other modules. As you can see in COMSO Multiphysics structure mechanics modules, you can use it to construct two-dimensional geometries, simulate two-dimensional structures, three-dimensional structures, shells. Also, if you can also use it to simulate cables, trusses, beams, for example, thick and thin-walled shells and plates, wires, because beams and cables are not the similar. They both can support tension, but both cannot support or cannot compensate compression at this point. So COMSOL can understand the difference between a beam and a cable or a wire. Some of the features you can find in COMSOL and the multiphysics between this structure mechanics module and other modules, for example, solid mechanics, shell, layered shell, membrane, beam, truss, which we talked about earlier, lump mechanical systems also. The other modules under the structure mechanics category, which is rotor dynamics. Some of the new features we have in COMSOL, which is pipe mechanics feature, where you can simulate the pipe mechanics, the pipe stresses or stresses in pipe in walls and based on external and internal pressures in pipe networks using COMSOL multiphysics. There is also the multiphysics between structure mechanics and heat transfer and AC/DC, which you can find in thermal stresses in nodes. We can also expand it to see that there is also the Joule heating effect. So you're combining three modules or three equations at the same point. Also poroelasticity, which is a combination between fluid flow and subsurface flow, I mean in fluid flow and structure mechanics. Magnetic restrictions, piezoelectricity, fatigue module. This is a separate module which you can also need structure mechanics to use, and so on. As I've said, you can find lots of multiphysics between structure mechanics and other modules, such as piezoelectric effect by combining AC/DC module or electrical current and structure mechanics. You can simulate the effect of an electrical current or electrical field on a piezoelectric material both ways. For example, you can apply potential difference across a certain material and see how it deforms, how certain stresses arise, or the other way, you can apply a certain pressure or a stress upon a certain material, piezoelectric material, and see what kind of electrical field develops in the material. You have also acoustic structure interaction, thermoelectric effect, or thermoelectric structure interaction. One of the very interesting features we have is the fluid structure interaction. You can simulate how a fluid interacts with a solid body, either one-way coupled or two-way coupled between the fluid and the solid. So we have the FSI, or fluid structure interaction. We have also the thermal structure interaction, which is a bit less than one step less than the thermoelectric structure interaction. So you're combining just the heat transfer part with the structure mechanics. You can see how heating a body or cooling a body affects it stresses inside the body, as we're going to see one of the examples we're going to do today. We have a question. Let me check a question first. Someone raised their hand. Can you type the question in the chat box, please? Okay. If you have any question, please raise your hand using the raise hand function in Zoom, and we can answer your question later. So now we're going to do some demonstrations of the module in action. We're going to use some of the features in the structure mechanics module and other multiphysics based on the structure mechanics module. The whole model is just a steel bracket. I'm going to import this geometry from another file, do some edits on it, and then we can later work with the physics or different kind of physics or different features we're going to use from the structure mechanics module. Let me start my console first. So now you should see my console multiphysics interface. I'm going to start with model wizard, 3-dimension. Let's start first with solid mechanics. So I'm going to go to structure mechanics, solid mechanics, add, select the study. First study we're going to use is station study. Click done. In the parameters, I'm going to apply a force to this bracket. So let's say the force is 100 newtons. I'm going to call it F1, 100 newtons. I'm going to apply force. In the geometry, right click on it, import. I'm going to import the file from my installation folder, so program files, the console 55, multiphysics, applications, and then I'm going to go structure mechanics. And this is my bracket. So this is my bracket geometry. I imported it from a different file. So to save time in constructing it, I'm going to do some edits to help us with or facilitate the meshing later. So I'm going to create a work plane on the ZX plane. And I'm going to go inside the plane. I can go create a smooth square like this using the sketch tool. So no, this is a big square. What I'm doing now is to specify a certain region which I'm going to use a certain type of mesh upon, while leaving the rest of the geometry with a certain different type of mesh. So I'm using this work plane to split apart the two regions, so not to create a very fine mesh upon all the geometry. So this is how I create my first square, and then I can extrude it. Go to work plane, extrude under geometry, and I can extrude it upon the z-axis for around 0.15 meters. Let's make it 0.12. Like that. So this is my first one. I would like to repeat this 4 times upon the 4 corners with the filling parts. So I can use either mirror as an operator. So I can go to transform, mirror. I'd like to mirror this object. I would like to have a point on my plane of reflection. So let's say my plane of reflection is going to be ZY. So a point on the plane of reflection is going to be 0 in X, 0 in Z, and it's 0 in Y. So let's take this one. Oh, no, it's not that. Just 0. Yes, like that. The thing is that I transformed my block from the right-hand side to left-hand side, so I can just use this box, keep input object. Now I have my 2 boxes this way. I can also use another mirror to mirror this first mirror. So I can go to transforms, mirror. I would like to mirror my first mirror, which is MIR1 here, like this, and mirror them on the YX plane. My YX plane is going to have the same, more or less, basic coordinates in the point of plane. So it's 0, 0, 0, and 0 in the XZ direction, 0 in Y, and 0 in X, same thing. But instead of having it in Z like that, I guess it's 1 here. Yes. Again, keep input object. Now I have my 4 corners covered in blocks. I can use then the Boolean partition and then use the partition domains. I would like to partition these domains. I'll just move something here, just a moment. I would like to partition it using these objects, like that. And then remove objects. So now I have a partition around the joints. I would like to just remove or minimize the size of this partition so not go into my through holes. So I can go back to geometry in the square part. I can minimize it like that. Yeah, so now it's out of my through holes. If I build it again all like that, if I go outside and can check it, build all, yeah, it's now fixed. Now I have my partitions around my geometry. Next, for materials, I can select a material from the library, add material. I'm going to build in. I can select steel, which is more or less the common material to build brackets from. So steel, and double click it to add. Since we have only one domain, so it's going to be selected automatically. Under structure mechanics, we have, for the first example, we have 2 constraints, just a point or 4 points, four bolts to fix it to structure. So these are my fixed constraints. I can go to physics, select boundaries, fixed constraints, and then I have to select the inner surface of these through holes. I can also use some of the definition tools I have here, which is called selections explicit. And the beginning of my geometry, I can select certain boundaries or certain domains and name them, and then I can automatically or quickly select them later. So now like that. Now I've selected my through holes, and under that I can maybe call them something else. Instead of explicit one, I can call them bolt holes, like that. So when I go to fix constraint from the selection menu, I can go select bolt holes. They're automatically selected this way. This is my fixed constraint. This is the part of the object which is anchored to an immovable boundary. Next, I can apply a boundary load in this area. So my boundary load is going to be on these faces here. I assume the load is going to be downwards, so I can apply it in the negative Z direction. So here, total force, negative F1, which we created earlier in the parameters. So the force is downwards. Next, I can go to mesh. I can build the automatic mesh, which is going to be like that. So I can optimize it more than that. So I can go to mesh. Instead of selecting physics controlled mesh, I can select user controlled and then select the swept mesh. I would like to sweep mesh on a certain domain, which is this, 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 and that. So anything outside the 4 blocks which I created earlier. I can select the source face to be this face. Nope. Switch the order of the mesh. So I would like to create my swept mesh first and then my tetrahedral mesh next. Like that. That's one way to do it. We can have better ways. We can optimize the mesh even more if we want to. So for example, for the swept mesh, I can create another size here. So maybe for this swept mesh, I can have a fine mesh, and for the tetrahedral mesh, I can have an extra or a finer mesh. So like that. And let's keep it as is, normal and fine. Yes. So going back to the study, I can just run it, click compute, wait for a couple of minutes until it's done. In the meantime, if you have any questions, please use the raise hand function or ask in the chat box. Now we have the results available. We can see that it's automatically created a stress with a deformation plot. Okay, I have a question here. Hello, can you ask your question? Please unmute yourself and ask a question, please. Or ask your question in the chat box, either way. Okay, if you can hear me, please ask your question either in the chat box or, yes, we have a question here. Yes, we can specify a size of the mesh. So if I go to my size node, I can go to custom and then specify the maximum element size, minimum element size, distribution, everything here. Now, this is introduction to comes from Multiphysics structural mechanics module. So if you look at the plot, here we have a stress plot, which includes, if we open it, yeah, the von Mises stress in Newton per meter square. I can change the unit if I want to megapascal, gigapascal, whatever. So megapascal, you can see the scale in megapascal. And you can see the stresses and deformation. As you can see, the deformation is exaggerated, so I can just disable it. So it's not visible like that. Yeah. Sorry. Disable. So this was my first plot. I can also slice into it. I can create, for example, a different plot, like a 3D plot, slice, use the same expression. So I can't remember expression, for example. I can try search for it in the replace expression tool. So von, yeah, solid.mises. In again megapascal if I want to plot. It automatically plotted multiple slices, which is 5 slices in the YZ plane. I can change the plane, so for example, the ZX plane, and for example, instead of 5, it can 20. Now I have multiple planes. That's one way to draw a slice plot. Okay, we can add more physics to this model. For example, if I wanted to have the same model to express thermal stresses, I can go to physics, add my heat transfer part. So add physics, added a new feature, which is heat transfer in solids. Double click. Now I've added my heat transfer in solids. I can add a heating surface or a heat source in this. So I can right click on it, heat flux. So let's say there's some heat coming from this area, which is around, for example, 10,000 watts per meter square. I can also specify a boundary heat flux, which is everything else except for the heat source. So except of these are the heat loss surfaces. So let's say convective heat flux, let's say it's 10 watt per meter square Kelvin. Yes, and then we can add the multiphysics, because if we didn't add the multiphysics, it is going to compute the solid mechanics alone, the heat transfer alone, without combining them together. So you will not see how heating it develops stresses. So thermal expansion, the multiphysics applied here on those domains, all domains. I can remove also the boundary load node, since I don't need it now. I would like to see just the heat stresses in this model, so disable. My model is still affixed to the to the anchor from this fixed constraint, which is still available here. And then I can run it again. Study, compute. Shouldn't take that long. Okay, this is the stresses for this model. We can also add a temperature plot. So I can go to results, 3D plot, surface plot, for example, and then place the expression for T, which is temperature in Kelvin. You can see the temperature gradient upon the whole surface. So from 310 Kelvin to 400 Kelvin. I don't like Kelvin. I can have degrees Celsius, Fahrenheit, whatever. From here, plot, you can see the scale changed in the legend. I can change the color of the legend, for example, to thermal. This is like a thermal camera. The coldest is the darkest, the brightest is the hottest or the warmest surfaces. I can reverse the color table if I want to. All of these tools are available under post-processing or the results part in COMSOL. So let's go back to the stresses part of our meso stress, which you have created. You can see these are the stresses developed near the holes, which are the fixed constraint holes, because they are anchored and they cannot move. These are the stresses developed because of heating or raising the temperature of the whole body. We can use the same model and add a temperature, the time-dependent study. So we can go to study, add study, time-dependent, and we can see how the temperature is rising throughout the body, for example, per second or per millisecond or whatever time domain we have. So in the time domain and the time-dependent study, we can select the time unit as seconds, for example, from 0 to 10 seconds. So we can use this syntax, which is range, start time, increment, and then end time, or use this range tool to specify from start 0, stepping of 1, and ending at 10 seconds. So it's 0, 1, 10. Compute. Now the study is computing for solid mechanics, heat transfer, and thermal expansion. I can remove this deformation part from my plots, and now you can see the stresses, same thing, but it's developing over time. So you can see the stresses increasing in the legend as color, or I can also put an annotation on the surface. So here I can put an annotation on this area. So it's around in the z direction 0.05, 0.05, x and y is 0. So this is 0.05. So let's put it at y to x. Yeah, negative 0. For example, 4. Negative 0.04. So almost there. 0.045. It's almost on the surface, so let's try to push it a little bit more. I don't have the exact coordinates, so just try here. So in the y direction, let's push it 0.01, negative 0.01. Yeah, so it's on the surface here. And the x direction 5, 5, yeah, maybe here. We can use a text to express a certain expression, so we can use this evaluation of expression tool. So we can type eval. Before we type eval, we can type first select our expression. So it's von Mises, and then open eval, open parentheses, and then the close parentheses after it. So these are the stresses upon this area. So whenever we change the time frame, the stresses will increase whatever unit I'm selecting. So it's Newton per meter square now, times 10 power 7, or e power 6. Depends on the scale you're looking at. So that's why one way to look through your plots. There's another way we can also edit our study to, for example, have our study 1, which is a stationary study, to compute just for the solid mechanics, which we did already without the multiphysics. But we have disabled our boundary load. We can enable it just for this study. So we can go to modify model configuration study setup steps. We can go to boundary load and enable it first here. Yes. So it's now enabled in my study. But as you can see, this is disabled, yes. And my math physics is disabled. So yeah, if I run the stationary solver, it's going to calculate the stresses upon just the solid mechanics node. While if I go to time dependent solver, I can go to modify model again, and now disable this one only. So just click on it and then select disable. So now my time dependent solver is going to solve the same model with heat transfer and everything, but without the boundary load. So instead of actually disabling the physics here on the model builder, we can disable it just for a certain solver or a certain part of the solver. And I'm going to get the same results after that. We can go to the heat temperature solution for the time dependent. For example, you can see the temperature rising. So let's play around with the legend. So surface, zoom out. My range, I need to set my range. So like that. So in 10 seconds, the maximum temperature I've got 297 Kelvin, while the minimum temperature was 293 Kelvin. So if I go back to 0, this is my first plot, or that time equals 0 second. I can now increase my seconds, my time, and see how it increases. I can compile this into a small movie or a small GIF by going to Results, Animation, Player. So my subject is temperature, HT, which is this one. And then since I have number of frames only 10 or 11, I think, so leave it automatically, it's going to detect it automatically. And then show frames is going to compile it now. If I click play, I can see it heating up. So if I increase the time domain and edit the number of frames here, I can have more frames and a longer movie with more heat transferring to the whole body. So that concludes our introduction to structural mechanics module for today. If you have any questions, please raise your hand or share it in the chat. Yes, we have questions here.